Hello, welcome to another module in this massive open online course on estimation for wireless communications. So in the previous module we have started looking at an example for FDE, that is frequency domain equalization, and we said as the name implies, equalization, that is removal of inter-symbol interference, is done in the frequency domain. This is similar to OFDM in the sense that before transmission of the block of symbols one adds the cyclic prefix. However, at the same time it is different from OFDM in the sense that we are not transmitting the IFFT samples of the symbols, rather we are transmitting the symbols directly after adding the cyclic prefix. Okay. So, we are looking at an example of FDE which stands for frequency domain we are looking at an example for FDE, that is frequency domain equalization, all right. And we said we are going to consider QPSK or quadrature phase shift keying QPSK symbols, which are basically x0 equals 1 plus j, x1 equals 1 minus j, small x2 equals minus 1 minus j, and small x3 equals basically your 1 minus j. These are basically your n equals 4. These are your basically n equals 4 symbols, and these are QPSK symbols, this is quadrature phase shift keying symbols. Remember, QPSK is constellation in which basically there are 4 symbols, 1 plus j, 1 minus j, minus 1 plus j, minus 1 minus j, right. So, these are the, this is the QPSK quadrature phase shift keying digital constellation with 4 symbols, and we are also considering a system, that is an FDE system with n equal to 4. You can think of this because there are no subcarriers really speaking in an FDE system. So, you can think of it as an FDE system in which the block size is capital N equal to 4. Okay. And now what we do, and as we said, these are directly the symbols in the time domain, not the samples, because in OFDM we transmit samples in the time domain. In FDE we directly transmit the symbols in the time domain, and therefore what we have is basically we have x0, x1, x2, x3, and to this we add the cyclic prefix. That is, realize here the cyclic prefix is directly added to the symbols, that is there are no samples. So, you take the symbols, block of symbols, add the cyclic prefix. Therefore, the transmitted symbols are given as, now all I have to do is basically x3 equals 1 minus j, x0 equals 1 plus j, x1 equals 1 minus j, x2 equals minus 1 minus j, and x3 is again equal to 1 minus j. And what is this? This is basically your block of transmitted symbols with cyclic prefix. This is your block of transmitted symbols with cyclic prefix, and this is transmitted over the 2 tap ISI channel yk equals xk plus 0.5 xk minus 1 plus vk. These are the, this is the 2 tap ISI channel with the tap h0 equals 1, h1 equals 0.5. These are the channel taps in the time domain. I hope everyone remembers that. Right. And therefore, now once you transmit the cyclic prefix added block of symbols, right, in the time domain, what you get is basically a circular convolution of the channel with the transmitted symbols. And once you take the FFT across the nth FFT point, you get capital YL equals capital HL times capital XL plus VL, all right. So, in time we have Y, let me just write this, we have Y equals H circularly convolved with X plus V, you take the FFT, that is in FFT domain you have capital YL equals capital HL times capital XL plus capital VL, where this is YLs are basically the nth FFT point of the output samples, yeah, nth FFT point of output samples your small yk. Therefore, capital Y of L we have seen yesterday, that is given as small l equal to 0 to n minus 1 or small k equal to 0 to n minus 1 yk e power minus j pi by 2 times kl. Okay. Now, we had also considered for the purpose of this example the received samples y0 equals 1, y1 equals half, y2 equals half, y3 equals 1, and what we do now is we take the n equal to 4 point, we take the n equal to 4 point FFT or basically your DFT. FFT is a fast algorithm to perform the DFT, which is the discrete Fourier transform, and we said that the samples across the various FFT points are y0 equals 3, y1 equals half plus half j, y2 equals half minus half j, and y3 equals I am sorry, y2 equals 0 and y3 equals half minus half j. Okay. So, we have the small y's which are the symbols, output symbols in the time domain. You take the FFT, the n point, that is n equal to 4 point FFT, you get the output samples across the various FFT points, or you can think of these as across the various sub channels in the frequency domain. However, since this is not OFDM, we really do not have the notion of sub carriers. So, it is better to simply think of these things as sub channels or simply your FFT points in the frequency domain. All right. And the capital H's, they are the channel coefficients across these various sub channels, and they are given by the 0 padded FFT of the time domain channel taps. Okay. So, I have your H0, H1, you pad them with zeros and you take the n equal to 4 point, n equal to 4 point FFT, and you get the channel coefficients in the frequency domain. You get the channel coefficients in the frequency domain. The channel taps are basically your H0 equals 1, H1 equals 0.5, and you take the FFT of this, you take the n equal to 4 point FFT of this after padding with zeros, and what you get is the channel coefficients in the frequency domain across the sub channels are, well, 3 by 2, H0 equals 3 by 2, coefficient across the 0th FFT channel or 0th FFT point, H1 equals 1 minus half j, H2 equals 1 minus half equals half, and H3 equals 1 plus half H3 equals 1 plus half j. And now what we said is basically in the across the lth FFT channel or across the lth sub channel we have we have YL equals HL XL plus VL. This is across your lth FFT channel, across let us say lth sub channel. Therefore, estimate x hat of the lth FFT coefficient across the lth sub channel is basically simply YL divided by HL. This is estimate. What is this? This is basically your estimate of FFT coefficient of transmitted symbols which are the small x's. This is estimate of the lth FFT coefficient. So, what is capital X hat L, right? Remember XL is basically the capital XL is basically the lth FFT coefficient of the transmitted symbols which are the small x's, small x0, small x1, small x2, small x3. Okay. So, now in the frequency domain you are estimating capital X hat of L, which is basically an estimate of capital X of L, that is the lth FFT coefficient of the transmitted symbols. Okay. So, therefore, capital X hat L we have said equals YL divided by XL. This is the estimate of the lth FFT coefficient of the transmitted symbols. Of the transmit symbols, we can now calculate the various estimates as follows. Capital X hat 0 equals y of 0, capital Y of 0 divided by capital H of 0, which is equal to, well, this is equal to capital Y of 0 is 3, that is something that we have already calculated. Capital H of 0 equals 3 by 2. You can see this from here, you can see that capital Y of 0 equals 3, capital H of 0 that is equal to 3 by 2. Basically, therefore, capital X hat of 0 equals capital Y 0 divided by capital H 0, that is 3 divided by 3 by 2, that is 2. Capital X hat of 1 equals basically you are again the very same thing, capital Y 1 divided by capital H 1. This is the capital Y 1, again to remind you, this is the output across sub channel L, sub channel 1, that is in the frequency domain. This is the channel coefficient for sub channel 1. Which is equal to basically half plus half j divided by 1 minus half j, and therefore, this can now be simplified as half plus half j times 1 plus half j divided by divided by 5 by 4, which is equal to 1 by 4 plus 3 by 4 j into 4 by 5, and this is therefore equal to 1 by 5 plus 3 by 5 j. Okay. And capital X hat of 2, capital X hat of 2 equals y 2 divided by capital H 2, but capital Y 2, remember the output across sub channel 2 is 0 divided by capital H 2 is half. So, this is 0, and finally, capital X hat of 3, that is estimate of the FFT coefficient of the estimate of the third FFT coefficient of the transmitted symbols is capital Y 3 divided by capital H 3, which is equal to half minus half j divided by 1 plus half j. equals, right, and this can again be simplified as using the properties of complex numbers as half minus half j times 1 minus half j into 4 by 5, which is equal to 1 by 4 minus 3 by 4 j into 4 by 5, which is equal to 1 by 5 minus 3 by 5 j. So, we have basically computed the estimates of the FFT coefficients of the transmit symbols, and these are now, to summarize, you have capital X hat of 0 equals 2, capital X hat of 1 equals 1 by 5 plus 3 by 5 j, capital X hat of 2 equals 0, capital X hat of 3 equals 1 by 5 minus 3 by 5 j, and what are these? These are the estimates of the FFT coefficients of the transmitted symbols. These are estimates of FFT coefficients these are the estimates of the FFT coefficients of the transmit. So, we have computed the estimates of the capital X's. The capital X's are the FFT coefficients of the transmitted symbols. We have computed the respective estimates, that is the capital X hats. Okay. So, now we have the estimates of the FFT coefficients of the transmitted symbols. Now, how to get the transmitted symbols themselves, that is estimates of the transmitted symbols, that is basically take the inverse FFT of this estimated FFT coefficients, right. So, the capital X's are given by the FFT of the small x's. So, if you take the IFFT of the capital X's, you will get the small x's, right. So, take the capital X hats, right, the estimates of the FFT coefficients, take the inverse FFT, and you get the estimates of the small x hats, that is the estimates of the time domain symbols, okay. And that is basically as simple as that. So, basically you have capital X hat of 0, capital X hat of 1, capital X hat of 2, capital X hat of 3. These are estimates of FFT coefficients. Of your transmitted symbols. Naturally, you have the estimates of the FFT coefficients. You take the IFFT, that is your n equal to 4 point IFFT, and what you will get is the estimates of the time domain transmitted symbols. You get the estimates of the time domain symbols, and therefore, let us do that now. So, we have basically your capital X hat 0 is 2, capital X hat 1 is 1 by 5 plus 3 by 5 j, capital X hat 2 is 0, capital X hat 3 is 1 by 5 minus 3 by 5 j, and basically now you take the IFFT of this, that is basically what we are saying is small x hat of k is given by the IFFT of the capital X hats of L equal to 0 to n minus 1, capital X hat L e to the power of j 2 pi k L divided by n, substitute n equal to 4, and what we have is basically small x hat of k equals 1 over 4, small l equals 0 to 3, capital X hat of L e power j 2 pi k L divided by 4, which is equal to 1 over 4 L equal to 0 to 3 capital X hat of L e power j pi by 2 capital X hat of L, a small x hat of k. Okay. Small x hat of k equals 1 over 4 summation L equal to 0 to 3 capital X hat of L e power j pi by 2 times k L. Okay. And therefore, now let us compute the estimate of the symbol 0 capital X hat of 0, you can simply see is 1 over 4 capital X hat of 0 plus capital X hat of 1 plus capital X hat of 2 plus capital X hat of 3, which is equal to 1 over 4 times 2 plus 2 by 5, correct, and therefore, this is equal to 1 over 4 into 12 by 5, which is equal to 3 by 5, that is small x hat 0, which is the estimate of the transmitted symbol 0 or the 0th transmitted symbol in the time domain, right, is basically 3 over 5. That is what we have just calculated, right. This is the estimate of the 0th symbol in the time domain. This is the estimate of the 0th symbol in the time domain. Okay. Small x hat of 1 equals 1 over 4 capital X 0 plus capital X 1 e power j pi by 2 plus capital X 2 e power j pi plus capital X 3 e power j 3 pi by 2, which is equal to 1 over 4 2 plus 1 by 5 plus 3 by 5 plus j 1 more 5 plus 3 over 5 j times j plus 0 plus your 1 over 5 minus 3 over 5 times 3 over 5 j times minus j, which is basically equal to 1 over 4 2 plus j by 5 minus 3 by 5 minus j by 5 minus 3 by 5 minus 3 by 5, which is equal to 1 over 4 2 minus 6 by 5, which is equal to 1 over 4 times 4 divided by 5, which is equal to 1 over 5, and this is small x hat of 1. Okay, that is the estimate. So, we have computed small x hat of 1. Here we have computed small x hat of 0. Let me just mark this clearly, small x hat of 0 equals 3 by 5, and small x hat, that is that symbol, that is the small x hat of 1, which is the estimate of the first time domain, that is small x hat of 1, that is the time domain symbol x of 1, small x of 1. Okay. Let us similarly compute small x hat of 2, that is the estimate of the time domain symbol small x of 2. So, small x hat of 2 equals 1 over 4, again simply substituting in that IFFT relation that we have capital X hat of 0 plus capital X hat of 1, just making sure that we have written the estimates. These should be the estimates, because what we are working with are really the estimates, capital X hat of 3. So, this is capital X hat of 1 plus capital X hat of 2, capital X hat of 1 into e power j pi plus capital X hat of 2 e power j 2 pi plus capital X hat of 3 into e power j 3 pi, which is equal to your 1 over 4 capital X hat of 0 minus capital X hat of 1 plus capital X hat of 2 minus capital X hat of 3, which is equal to basically 1 over 4 2 minus 1 by 5 plus 3 by 5 j minus 1 by 5 minus 3 by 5 j, which is equal to 1 over 4 2 minus 2 by 5, which is 1 over 4 times 8 divided by 5, which is equal to 2 by 5. Therefore, small x hat of 2, estimate of symbol small x of 2 equals basically 2 by 5. So far we computed small x hat of 0, small x hat of 1 and small x hat of 2, and now all that remains is to compute small x hat of 3, and that can also be computed similarly. Let us just complete that. Small x hat of 3, which is the estimate of the time domain symbol small x of 3, is 1 over 4, well, x capital X hat of 0 plus capital X hat of 1 e power j 3 pi by 2 plus capital X hat of 2 e power j 3 pi plus capital X hat of 3 e power j 9 pi by 2, which is equal to your 1 over 4 capital X hat 0 minus j capital X hat of 1 plus j capital X hat of 3. You can see we are avoiding capital X hat of 2 because that is 0 anyway, okay. And therefore, this is equal to 1 over 4 2 minus j times 1 over 5 plus 3 over 5 j plus j times 1 over 5 minus 3 over 5 j, which is equal to 1 over 4 times 2 plus 3 by 5 plus 3 by 5, which is 1 over 4 times 16 divided by 5 equals 4 divided by 5. Therefore, small x hat of 3 equals 4 divided 5. 4 over 5, we have computed the estimates of the various symbols in the time domain, small x hat of 0, small x hat 1, small x hat 2, small x hat 3, which was the aim, right. So, basically this is frequency domain equalization, right. We have to ultimately compute the estimates of the transmitted symbols in the time domain, okay. So, now let us write these things down again. Let us again write these things down. So, the symbol estimates, finally one can write the symbol estimates in the time domain So, the symbol estimates in the time domain are given as small x hat of 0 equals 3 over 5, small x hat of 1 equals 1 over 5, small x hat of 2 equals 2 over 5, and small x hat of 3 equals 4 over 5. So, these are the estimates of symbols transmitted in the time domain. estimates of the symbols transmitted in the time domain, and that completes your FDE, which is basically the frequency, that completes this example of FDE, which is frequency domain equalization. And as you have seen, which is the same point that we are stressing since the beginning, that it's similar to OFDM, at the same time it's different. Similar in the sense we add the cyclic prefix prior to transmission, however it's different from OFDM because we are not transmitting the IFFT samples of the symbols, rather we are transmitting directly the cyclic prefix added symbols. So the previous modules we have looked at the theory of FDE, which is frequency domain equalization, and in this we have completed a simple example which illustrates what is the transmission and how is the equalization done in the frequency domain, followed by basically how do you reconstruct the estimates or how do you find the estimates of the transmitted symbols in the time domain, alright. So this comprehensively basically explains or elaborates on this paradigm of frequency domain equalization through an example, alright. So please go through this again to understand it completely and thoroughly, alright. And so we will stop this module here on frequency domain equalization, and I would like to also remind you that frequency domain equalization is basically much more, it's preferred compared to time domain equalization because of its low complexity. Basically it involves only IFFT, similar to OFDM, it involves only IFFT and FFT operations, but there is no matrix inversion, unlike the time domain equalizer or basically the zero forcing equalizer, which actually involves the computation of a matrix inverse. Okay. So we will stop this module here and we will explore other aspects in the subsequent modules. Thank you very much.